Howdy everyone, we're here to chapter 10 with gases in AP Chemistry. A lot of this stuff is going to be review from Chem 2 where we had the gas laws, the equations have not changed. We're just going to add in a few little things here and there, but this chapter should be a decent amount of review, let's just dive right into it. So some reminders about what are gases. No matter what the specific gas is, they all have similar properties. Usually it's non-metallic compounds. Simple formulas, low molar masses, because if the molecules get too big, as we'll see in chapter 11, then they start sticking to each other. Gases tend to expand to fill containers. They can be compressed or expanded. They have very low densities. And if you take two or more gases, they will always form a homogeneous mixture. They will always mix evenly given enough time. All right, here's some common gases. You don't really need to memorize many, just a few to note. We have carbon monoxide, carbon dioxide, we know about those. Hydrogen sulfide, rotten egg smell, a lot of sulfides have that. N2O, laughing gas, various gases, whatever. The properties that we're going to be using in all our equations for this chapter. We have to know temperature. Temperature must be in terms of Kelvin for all gas laws, so please remember that. Temperature must be Kelvin. Pressure has a bunch of different units. We'll talk about that on the next couple slides. Volume, officially we're supposed to use cubic meters, but pretty much everyone says now we can convert units. So liters or milliliters are what we normally use there. And then number 4, we need the amount of gas, usually expressed as number of moles. So these are pretty simple, and the equations are pretty simple. So the key thing that you have to watch out for, to make these simple things, test-worthy, they make them annoying. They'll give you temperature in Celsius and make you change it to Kelvin first. They'll give you volume in milliliters, but you have to change it to liters first. They'll give you grams of a gas. Oh, okay, got to go from grams to moles. So they'll try to pile on busy work to see, did you forget to do the little things? Because the gas law equations themselves, usually pretty simple. Just plug in your numbers, see what your equation gives you. All right, let's talk about pressure a little bit. Pressure, strictly defined from physics, is a force over an area. And so when we think about it, here on the surface, we are living at the bottom of an ocean of air, and all that air on top of us is being pulled down by Earth's gravity onto us. Well, that's the force. And then we just have some area. Maybe it's a square meter here. Maybe it's a square inch, right, for that. But that's what atmospheric pressure is. All the weight of the gases in the air above us being pulled down on top of us. So they say here, for about a square meter, it's about 10,000 kilograms of mass, which, hey, we're holding up roughly a couple thousand kilograms of mass. I feel stronger. How about you? All right. Well, let's talk about the units. Officially, we should use the Pascal. That's the SI unit. 1 Pascal is 1 Newton per meter squared. But we don't really use newtons very much. I mean, if you're in physics, you do, but we should use pascals, but we want other terms. Because it turns out for an average pressure, we're in the 100,000 Pascal range. Well, that's a big number. So then we say, oh, well, what about a bar? Well, we get barometer, so bar for pressure. Well, that's 100,000 pascals, 10 to the 5th, or let's use metric prefixes, 100 kilopascals. All right, great. Now, we can deal with 100. We can deal with 1. We have things called millimeters of mercury, or torr. They are literally the same thing. In the case of millimeters of mercury, it is literally the height of a column of mercury. So how many millimeters of mercury in a glass tube that's been evacuated does the mercury get pushed up? And so that's how barometers were created. They were created by an Italian scientist named Evangelista Torricelli. That's where torr comes from, Torricelli. And he did this to show, it's not that we suck liquid up the tube, it's that the atmosphere pushes it up the tube. And so with the millimeters of mercury, we're saying how high does the mercury get pushed up the tube? Same thing happens with a straw. We don't suck the air or the liquid up a straw. We let the atmosphere push the liquid up the straw into our mouths. Anyway, these numbers for atmosphere, these are the equalities. And these, at least the ones that you need for the AP test, are given to you on the AP test, which is usually the ATM, either torr or millimeter. Maybe they give both. Just remember they're the same. And I'm pretty sure they give you the kilopascal one. Notice here for the 760, there's no decimal point. That's because these are considered exact conversions. One ATM is exactly 760 millimeters of mercury, so there's no limit to sig figs there for calculations. The 101.325, that's 6 sig figs. That's an approximation. All right, so we can convert between them. Those numbers are given. Again, that's the annoying bit. Maybe they'll give us millimeters of mercury, but we need ATM. Okay, we got to spend a second, convert it first, then we can plug it into our equations. All right, well, the last thing here before we get to the equations with a manometer, this is when you're measuring the difference in pressure. So you have a U-shaped tube filled with mercury, and so if the same thing is hooked up, or the same pressures on both sides, the mercury will be equal, right? Because there'll be, equal pressure, equal height. If one end pushes harder, maybe pressure of gas in a container pushes harder, maybe the atmosphere pressure is pushing harder. But whichever side is pushing harder will push the mercury down on that side of the tube and up on the other. And then this difference in height can tell us, well, what's the difference in pressure? So if we say, okay, this one's 103.8 and this one's 136.4, well, that's a difference of what, 32.6? Yeah, I think so, 32.6. Well, that means whatever the air pressure is, this gas pressure must be 32.6 millimeters of mercury higher. And when they're measuring millimeters, that's why we use a mercury tube, because again, it is literally how many millimeters of mercury. So we can adjust based on the height. If it's lower on the atmosphere side, then we would subtract it, or you could just say, oh, it's a negative height. So atmosphere minus the height gives us the gas. But that's just the difference in gases based on the difference in the mercury heights. Difference gives you the difference in pressure. All right. Standard pressure, when we say standard conditions, so that things can be compared all around the earth in different days, different weather. Standard pressure is 1 atmosphere, or the 760 torr, 760 mercury, or 101.325 kilopascal. So all those things that are equal to 1 ATM, that's standard pressure. So we usually use ATM, but depending on what units they give you, you might want to use one of these other numbers to make life a little bit easier. All right. Now let's talk about our gas law. So now that we've got pressure and volume and temperature and amount, how can we plug these in? So we'll talk about these as we go. Boyle's law says that the volume of a fixed quantity of gas at constant temperature, so notice T doesn't change, the amount of gas doesn't change, it's inversely proportional to pressure. So that means as we go up and the pressure decreases, the volume must increase. So the balloon gets bigger because the pressure has dropped. So Boyle's law, what he actually said in the 1600s, was that the product of pressure times volume was a constant. But if we have constant temperature and constant amount, we can rewrite this to say P1 times V1 equals P2 times V2. And so the graph, well, pressure versus volume will be this curved graph. And if you had Chem 2 in a non-shutdown semester, you would have done this lab and seen, oh yeah, we made this curved graph. But that means if you do the inverse, volume versus 1 over pressure, that will be a straight line. So just a little bit of trick there of how do we graph things. This is the classic shape of a 1 over x graph, or if it's inversely proportional. So when we do 1 over pressure, that's how we get a straight line. So that's Boyle's law, just P1 V1 equals P2 V2. Make sure you know that one because they're not going to give it to you on the test. The next one is Charles' law, which says the volume of a gas at constant pressure is proportional to the absolute temperature. So if we take a balloon and cool it down, the volume shrinks. If we take a balloon and heat it up, the volume gets bigger. So he said the volume of some container must be equal to a constant times the absolute temperature. And so we get this equation, V1 over T1 equals V2 over T2. And so here's actually how we came up with Kelvin. This is how we got the absolute temperature scale. They said, hey, we're measuring everything in Celsius, and we notice we get this really nice straight line from the data, but then things get so cold that they don't say gases anymore. They turn into liquids. Well, if we extrapolate, if we just follow this line back, where does it hit zero volume? And it would happen right around negative 273. And from better calculations now, we know it's negative 273.15 Celsius, if we're not rounding. But that's how we got that number, because, again, we can't reach absolute zero. This is how we extrapolate it to get a pretty good estimate of what it would be. All right, again, know this equation, but it's not given on the test. We'll fix that in a little bit. Gay-Lussac's law. Now in Chem 2, we taught this as that pressure and temperature are also proportional, just like Charles' law. We said P1 over T1 equals P2 over T2. Now there's some issues with that, or not issues, it's there's some debate of, is that really what Gay-Lussac said? Because he said other stuff about gases, and that's what this slide's about. There was another guy who said stuff like that, and it's weird, like, well, who should get first attribution, and who gets credit? It's a mess. So in Chem 2, we learned Gay-Lussac's law as P1 over T1 equals P2 over T2. You should still know that one. But this is another law that Gay-Lussac said, that said at a given temperature and pressure, the volume of gases that react with each other is in small whole number numbers. It's a whole number ratio for what those volumes should be. So 2 volumes of hydrogen and 1 volume of oxygen make 2 volumes of water. This is a lot of times in a recipe, right? 2 parts flour to 1 part sugar. Well, what's the part? Could be a cup, could be a pint, could be a quart. Doesn't matter. As long as they're equal parts, it'll still be the same whole number ratio. Now, he didn't know this at the time, but this was early stoichiometry, right? It's the whole number balancing that we're doing when we talk about the same volumes of gases. So this leads us to Avogadro's law, which says that the volume of a gas at constant temperature and pressure is directly proportional. Now, he would have said the number of particles. If we update for modern time, it's proportional to the number of moles. And so we say at STP, remember that's 1 atm and 0 Celsius, any gas, 1 mole of it will be 22.4 liters. So here we go. 1 mole of helium is 4 grams, but it's 22.4 liters at 1 atm and 0 Celsius. Nitrogen, 28 grams is 1 mole. So at 1 atm and 0 Celsius, it will be 22.4. 1 mole of methane is 16 grams. At STP, it'll be 22.4 liters. So they're all the same. What Avogadro said is here that the volume is a constant times some number of particles. So if we rewrite this now knowing about the mole, V1 over N1 equals V2 over N2. All right? And so, again, Avogadro didn't know about this. He just said it was the number of particles that was important. That's why we call it Avogadro's number. He didn't come up with that number. He just said the number, whatever it is, must be important. So when we kind of discovered what that number was, the 6.02, we named it after Avogadro in his honor. All right. Now, we can combine these gas laws to get what we call the combined gas law. And so the PowerPoint here actually didn't have a slide for this. I had to create one. And in your book, they just kind of put it as a little afterthought, but it's really useful. That P1 times V1 over T1 equals P2 times V2 over T2. So that's combining Boyle's law, Charles' law, and what we learned in Chem 2 is Gay-Lussac's law into one thing. The AP test used to give this equation. The last few versions of the test, they have removed this equation. So this is the one to memorize. Because if you know this equation, then you say, well, wait a minute. They said constant temperature. Well, temperature crosses out. Oh, P1 V1 equals P2 V2. And you've got Boyle's law without having to remember that one specifically. Or, oh, they say constant pressure. Pressure remains unchanged. Okay, cross out P1 and P2 because they would cancel out. Oh, hey, now I've got V1 over T1 equals V2 over T2. It simplifies the Charles law. So if you can memorize this one equation, you can then use it for the other more simplified ones without having to memorize everything. All right, so that's one thing that we can do by combining those other simpler laws. The other one we can do by combining those simpler ones is the ideal gas law, where we say, okay, volume is inversely proportional to pressure, volume's direct to temperature, volume's direct to amount. If we combine these, we say, okay, volume is proportional to amount times temperature over pressure. Well, if we reorganize it and throw in a proportionality constant that for once we don't just call K, we call it R, the gas constant, we get the ideal gas law. PV equals nRT. And so that's what you're used to again from Chem 2 is the ideal gas law. Pressure times volume will equal the amount of gas times the gas constant times the temperature. Again, got to be Kelvin for that. R actually makes some other restrictions on what units can be. So we'll talk about that here. This ideal gas constant, it makes it an equality, not just a proportion. So PV equals nRT. Now, the units that we use for R make it have a different value, but these are all equivalent. It's just, well, which units are we using? So the one we used most often in Chem 2 was this one, 0.08206 liter ATM divided by mole Kelvin. I know there's dashes in there. That's not a minus. That's kind of a multiplication. It's liters times ATM, moles times Kelvin. All right? But in one little part of Chem 2, depending on which class you had, you might get this, that sometimes we use 8.314 joules per mole Kelvin. You say, well, why are these numbers different? Well, it's really related here. You go from liters to cubic meters for volume. You go from ATM to pascals. And when we use those conversions, that, 1 ATM is 101,325 pascals. And 1 cubic meter is really, I'm trying to remember how many liters that is. It's a large number. It's like 10,000 liters, I think. Something around there. Well, actually, let me think about that. If 101,000... No, sorry, it's about 1,000 liters. No, that's right. Might be higher. Anyway, the upshot is when you convert those, you end up multiplying by 101.325. So it gets you from 0.08206 to 8.314. What you need to remember is these numbers are equal, just in different units. And the nice part is this number, this top one, this second one, and I believe even this bottom one are given to you on the AP test reference sheet. So you never need to memorize any of these numbers. They are given to you for when you need to use them. You just maybe have to figure out, wait, do I need to use one, and which one do I use? That's the trick, but that's going to be based on, well, what unit am I in? But these top two are the most commonly used. And for gas laws, we're going to use this top one mostly. We'll use liters times ATM, moles Kelvin. That means for the ideal gas law, PV equals nRT, our volume should be in liters, our pressure needs to be ATM, and our amount needs to be moles, our temperature needs to be Kelvin. So again, this is the busy work. Maybe they gave you milliliters, convert to liters first. Maybe they gave you pascals or kPa or torr, convert it to ATM first. Maybe they gave you grams, get it to moles. Maybe they give you Celsius, get it to Kelvin. So do all that pre-work and then plug it in and use this number for R. All right, well, what can we do with the ideal gas law? The combined gas law with the 1 versus 2, well, that's good for a before and after. With this one being PV equals nRT, well, that's more of a instant snapshot. At this one moment in time, the pressure, the volume, the amount, and the temperature are all these values. So how can we use that? One of the main uses is to figure out the density of a gas. If you say, well, density is mass per volume. Well, we can do moles per volume, and that's close, because then we can get to mass from the moles. That the number of moles times the molar mass equals the mass, right? That's normal. Well, if we rearrange that for N, we could say N equals the mass divided by the molar mass. And then we can plug that in and say, okay, the M goes in there for N, and then instead of dividing by the molar mass, we cross-multiplied, the molar mass ends up here. And since M over V, mass per volume, is density, we can say density equals the molar mass times the pressure divided by the gas constant divided by the temperature. Right? And so that's using the ideal gas law, just subbing in for moles to say that moles is the mass divided by the molar mass to get density there. All right, so that's one thing. So you say, oh, what is the density of oxygen at a certain condition? We'll say, well, what's the molar mass of oxygen? What's the pressure they gave me? Plug in R. What's the temperature they gave me? They'll have to give you pressure and temperature. You can plug those in, make sure you have the right molar mass, and then just solve for density. All right? If we're going the other direction, we can say, well, wait a minute. What if we know the density? What if we know the mass and the volume and temperature and pressure? We can plug that in and get the molar mass if we rearrange that equation. So that's actually what we did in Chem 2, again, if you did that lab, where we took the information, said we knew the temperature of the gas. We knew the mass of that liquid, we expanded to fill the flask that had a aluminum foil on top, and then we let it cool down and we measured how much mass was in there. We recorded the air pressure, we recorded the other stuff, and we plugged all this in, and we were able to solve, well, what's the molar mass of the unknown gas, even when we don't know what it is. So that's another common problem that we'll get, where you'll say, plug in the experimental data, figure out what the molar mass is, and then maybe an AP free response question is, if these are your possible gases, which one do you think it is? And you'll say, well, which one has that molar mass? Right? The last thing we can do with the ideal gas law is, because we can solve for moles, because we can solve for N, we can use it for stoichiometry, right? Because with stoichiometry, it was always first step, get to moles, second step, switch moles, third step, get to your answer. Well, that's what's going here. Oh, we can use gas data to solve for N. We can plug in the pressure, plug in the volume, plug in the temperature, solve for N. Then from that, using our balanced reaction, we can get to moles of the other chemical. And then from that, we can get to our answer. Maybe we go to grams using molar mass. Oh, but maybe we'll use the ideal gas law again. Or maybe the first step will use molar mass to get from grams to moles, then go to other moles, then use the ideal gas law here to get pressure or volume or temperature, whatever they ask for and whatever they give us the information for to solve. All right, so we can do that. It says we can relate volumes to gases. This is that Gay-Lussac law that they were talking about earlier. We say, well, wait a minute. If we have to use the ideal gas law in the first step, and we have to use the ideal gas law in the second step, and it's the same conditions, then the pressures cancel out, the temperatures cancel out, the volumes cancel out, everything's canceled out except for what's my mole to mole ratio, the balance coefficients. And that's where they're saying, oh, when you're going from volume of one chemical to volume of another gas, it had to be a whole number ratio, because our balancing has to be a whole number ratio. All right? And then a reminder, at STP, molar volume is 22.4 liters per mole. So if they tell you STP, you don't have to use ideal gas law. You can just say the summary, oh, it will be 22.4 liters per 1 mole based on 1 ATM and the 273.15 Kelvin and our gas constant of the 0.08206. So 22.4 liters per mole, that's just, if we plug that in ahead of time, let's just save that number when it's at STP. All right, so there's the main uses of the ideal gas law. We're going to stop there because that, other than the density stuff, probably would have been all review from Chem 2. So we'll stop there. We'll bring in new stuff in the next section. I'll see you there.